Okay, in this problem we're asked to find I0 of t in the network below using node equations. We'll utilize our problem solving strategies for S-domain circuits and also the one for nodal analysis. So if we look at our problem solving strategy for S-domain circuits, step 1 deals with the initial conditions. And if I look at my circuit, I notice this source is 2u of t, so it's not turned on for t less than 0, and this one's 12u of t, so it's not turned on for t less than 0. So from that we can conclude that the initial capacitor voltage is 0 and the initial inductor current is 0. So both of those initial conditions are 0. So now we're ready to move on to step 2, and in step 2 of our strategy we're going to draw the S-domain circuit. So there's our S-domain circuit, and to do nodal analysis, if we look at our circuit, we've got 3 nodes, 1, 2, 3. I'm going to pick this node as a reference, and I'm going to label this one V1 of S, and this one V2 of S. And if we look, in this case, we'll have a supernode because we have a voltage source connected between 2 non-reference nodes. So we have 2 node voltages. V1 and V2. So that's going to mean we got to write 2 equations. And if we look at our circuit now, we've got the node voltages defined. I0 of S is V2 of S over 2. Okay, so now, with nodal analysis, we know we have a voltage source. We're going to have a constraint equation. Okay, so our constraint equation for the supernode is V1 of S minus V2 of S is equal to 12 over S. So that's one of our 2 equations. Now, our second equation we're going to get by applying KCL at the supernode. And the supernode is shown by this blue boundary here. So here's the supernode, and what we'll do is we'll sum currents leaving the supernode. So if we look at the current leaving through the capacitance, the current there is V1 of S divided by 1 over S. We'll have a current leaving through this inductor. That'll be V2 of S over S. Then we have a current leaving here. That's V2 of S over 2. Okay, so we're going to sum currents leaving through the impedances and set to equal the sum of currents entering from the sources. So this current source is entering, so this is 2 over S. And here's our second equation. So now our task is going to be to solve these 2 equations. Now if we look, for instance, in really we need to solve for V2. So let's take this equation, let's rewrite it where we can have V1 expressed in terms of V2. So we have V1 of S is going to be V2 of S plus 12 over S. And we're going to get ready to substitute that into this equation. So let's start our work. So here we'll have this first term S, V1 of S. And then if we collect up these terms, we'll have 1 over S plus 1/2 times V2 of S is equal to 2 over S. So now we're going to have to work through the math. So one of the things that we'll do now is we'll take and substitute this in for V1. So now we'll have S times V2 of S plus 12 over S. Then we'll have 1 over S plus 1/2. V1 of S is equal to 2 over S. And again, now we just have to work on the algebra sum. And that should have been a V2 over S up here. We can see where we corrected that. Okay, now we're continuing to, so now we have S plus 1 over S plus 1/2 times V2 of S is equal to 2 over S minus 12. And now let's multiply through by S. So now this becomes S squared plus 0.5 S plus 1 times V2 of S is minus 12S plus 2. So then V2 of S is minus 12S plus 2 over S squared plus 0.5S plus 1. And if you remember, I0 is 1/2 V2 of S, so then I0 of S is minus 6S plus 1 over S squared plus 0.5S plus 1. So now there's an expression for I0. So now we need to do the inverse Laplace transform. So if we start off with I0 of S minus 6S plus 1 over S squared plus 0.5S plus 1. So now let's look at the roots of our characteristic equation. And let's use the quadratic formula. So now S is equal to minus 0.5 plus or minus the square root of 0.5 squared minus 4 times 1 over 2. So then the roots become minus 0.25 plus or minus J 0.98.9682. And that's, if you look, that comes out from this square root of 0.5 squared minus 4 square root. That's going to be a negative number, so that's where how we get the J. So now I0 of S, then we'll look at the partial fraction expansion. K1 over S plus 0.25 minus J 0.9682 plus K1 conjugate over S plus 0.25 plus J 0.9682. So then K1 we're going to multiply through by this term. So we'll have minus 6S plus 1 over S plus 0.25 plus J 0.9682 evaluated at S equal minus 0.25 plus J 0.9682. And when you do the math here, this turns out to be 3.266 at an angle of minus 156.72 degrees. Okay, and if we go back and look at the chapter on Laplace transforms, we can see that when we have complex conjugate roots, then I0 of t is 2, And we have 2 times 3.266. Okay, well there's a 3.266 that we got when we did the partial fraction expansion. We have e to the minus 0.25t cosine 0.9682t minus 156.72 degrees u of t amps. And if we go through and just write this out, we have 6.532 e to the minus t over 4 cosine, and this 0.9682 is the square root of 15 over 4 t minus 156.72 degrees u of t amps.